Welcome to today's journey through space and time, as we unravel the mysteries of the cosmos with the James Webb Space Telescope. Our quest will reveal new insights into the universe's earliest days and challenge our understanding of cosmic evolution. From the distant realms of exoplanets to the enigmatic supermassive black holes, and tracing back to the birth of the first stars and galaxies, the James Webb Space Telescope is revolutionizing our perception of the universe. It's unveiling cosmic wonders in unprecedented detail, transforming our understanding of the cosmos. Peering through cosmic dust clouds, it captures light from the most remote corners of the universe, a feat never achieved before. Yet, as the James Webb Telescope continues to unravel mysteries from the universe's infancy, it is also unearthing new, perplexing questions. This modern marvel, akin to a time machine, has recently uncovered enigmatic primordial galaxies that challenge existing cosmological theories. Join us on a journey as we delve into the latest astonishing findings of the James Webb Space Telescope discoveries so profound they might just overwhelm your understanding of the universe. Our universe, aged at about 13.8 billion years, has long been studied through the oldest light ever observed. This light was first detected by NASA's Cosmic Background Explorer (COBE) mission, launched in 1989. COBE's mission was to measure the cosmic microwave background, the residual radiation pervading space, birthed mere thousands of years post-Big Bang. The James Webb Telescope, engineered for deeper cosmic exploration, focuses on a period when the universe was approximately 100 million years old, a critical era of the formation of the first stars and galaxies. Researchers are optimistic that the telescope will yield unprecedented insights into these earliest galaxies and supernovae, further illuminating our understanding of the universe's genesis. Generated by the earliest stars of the universe, the James Webb Space Telescope, with its large aperture and infrared capabilities, has opened a new chapter in astronomy. For the first time, it allows experts to investigate the era of galaxy formation in detail. This information is crucial for astronomers to validate their theoretical models about the universe's evolution. One of the most striking recent discoveries by the James Webb Space Telescope is that the majority of the universe's ancient galaxies were enveloped in brilliant gas clouds. These clouds shone more intensely than the stars forming within them. This finding could be key in addressing a mystery that has the potential to revolutionize our understanding of cosmology. Emerging as early as 500 million years after the Big Bang, some of these early galaxies exhibit a luminosity so intense that it defies current cosmological explanations. The brightness observed should only be associated with massive galaxies, similar in star count to the Milky Way. Yet, these galaxies appear to have formed in a much shorter time frame than our galaxy. This challenges the foundations of our understanding of galaxy formation and even the standard model of cosmology, which suggests that a few million years post-Big Bang, energy transformed into matter, gradually leading to the formation of the first stars. However, with the advent of the James Webb Space Telescope, an abundance of such luminous stars has been observed, exacerbating the existing crisis in cosmology. While it poses a challenge to the prevailing cosmological model, the James Webb Space Telescope also offers potential solutions to some of the most profound mysteries about the universe. Based on the data it has gathered, astronomers using the James Webb Space Telescope have potentially unraveled a mystery surrounding the early universe. They've identified a large cluster of galaxies, about 12 billion years old, where almost 90% are enveloped in brightly shining gas. This glow was ignited by the light from nearby stars, spurring rapid star formation as the gas cooled. This significant finding is set to be published in the Astrophysical Journal. Lead author Anu Gupta, an astrophysicist at Curtin University in Australia, explains that their research demonstrates how interactions with neighboring galaxies are key to the extraordinary brightness observed in these early galaxies. These interactions likely catalyzed a surge in star formation, possibly explaining why early galaxies appeared more massive. This revelation was made possible through data gathered by the Webb's Advanced Deep Extragalactic Survey. Utilizing 3 of the telescope's instruments, the survey captured infrared images of galaxies and analyzed their spectra. By examining the light frequencies emitted by these galaxies, researchers identified spikes in emission features, a definitive indication that the gas was absorbing light from adjacent stars. Astronomers using the James Webb Space Telescope have shed light on a fascinating aspect of the early universe. Anu Gupta, an expert in the field, explains that while gas alone cannot emit light, the intense radiation from young, massive stars in early galaxies is just right to energize the gas, causing it to glow. This phenomenon was prevalent in early galaxies, which were rich in young stars. When the team compared the emission spectra of these ancient galaxies with those found in more recent ones that populate our current universe, they discovered that only about 1% of these newer galaxies shared similar characteristics. This comparison is crucial, as Gupta points out, for understanding the earliest galaxies and the genesis of the universe's chemistry. Gupta emphasizes the significance of these findings for our comprehension of the universe. Most chemical elements, apart from hydrogen and helium, originated in the cores of distant stars. Understanding the conditions of early galaxies and stars is essential for a deeper understanding of our own world. These groundbreaking discoveries reinforce the James Webb Space Telescope's role as a time machine revealing the story of our cosmic origins. But with every answer, new questions arise. The telescope's recent observation of a galaxy resembling our Milky Way, existing when the universe was merely 2 billion years old, challenges current theoretical models of galactic formation. Named Sears 2112, this newly discovered spiral galaxy exhibits a bar of stars and gas cutting across its center, reminiscent of the Milky Way's structure. This similarity raises intriguing questions about galactic formation processes. Scientists believe that, like the Milky Way, Sears 2112's bar functioned like a cosmic funnel, directing gas to the galaxy's heart and triggering star formation. This discovery not only provides insights into the early universe, but also challenges our understanding of how galaxies like our own came to be. Previously, astronomers believed that the presence of a barred structure in a galaxy indicated a mature stage in its evolution, typically seen in older galaxies that had reached full development. This was thought to occur only in galaxies existing around the midpoint of the universe's evolutionary timeline. Past observations from the Hubble Space Telescope supported this, showing that early galaxies with barred structures were exceedingly rare. However, new data from the James Webb Space Telescope is challenging this assumption. It suggests that barred spiral galaxies might not need extensive periods to develop. The discovery of the spiral galaxy Sears 2112 is a prime example. This galaxy, which bears a resemblance to our own Milky Way, was already in existence 11.7 billion years ago, when the universe was just 15% through its current age. Luca Costantine, an astrophysicist at the Centro de Astrolog A in Madrid and the lead author of the study, highlights the capabilities of the James Webb Space Telescope. It can gather 6 times more light than Hubble, allowing astronomers to observe more intricate details in distant galaxies. Sears 2112, observed at a redshift of 3, provides a glimpse into the universe when it was approximately 2100 million years old. This means the light from this galaxy has been traveling through space for billions of years before reaching us, offering a unique view into the past of the universe. The light from the galaxy, Sears 2112, took an astonishing 11.7 billion years to reach the James Webb Space Telescope, making this discovery particularly surprising. Galactic bars, like the one observed in Sears 2112, are found in about 2/3 of all spiral galaxies. However, it was previously thought that such structures only began to form around 4 billion years after the universe's inception. The study of detailed morphologies of distant galaxies, is crucial for understanding their history and opens new avenues in the research of galaxy formation and evolution. Cristina Cabello, a co-author of the study and a researcher at the Institute of Particle Physics and the Cosmos in Madrid, highlighted the significance of this finding in a statement. The presence of a bar in CIRS 2112 directly challenges existing theoretical models, which did not anticipate that the early universe's conditions would allow for the formation of barred galaxies. Luca Costantine, the lead author, points out the difficulty in reconciling these observations with theoretical predictions from cosmological simulations. These models currently struggle to reproduce such systems in the epochs observed. This discrepancy suggests that there might be a key physical component missing in our current understanding. Further studies like this are not only illuminating the processes of galaxy formation, but are also reshaping our understanding of the role of dark matter in the universe. In the study of the early universe, astronomers estimate that a staggering 85% of all matter is dark matter, a mysterious substance that eludes direct observation because it does not interact with light. Dark matter is believed to have played a critical role in galaxy evolution and star formation, starting as early as 380,000 years after the Big Bang. However, findings from this new study, particularly regarding the galaxy CIRS 2112, indicate that galaxy evolution, at least in this instance, was primarily driven by ordinary matter rather than dark matter. This was the case when the universe was about 2 billion years old. The structure of CIRS 2112 reveals that the contribution of dark matter to its galactic bar is minimal, with normal matter being the dominant component. According to co-author Jairo Abreu, a researcher at the University of La Laguna, this discovery affirms that the evolution of CIRS 2112 was chiefly influenced by baryons, the ordinary matter that constitutes everything we are familiar with, as opposed to dark matter, despite its abundance in the early universe when it was only at 15% of its current age. This insight is a testament to the transformative impact of the James Webb Space Telescope. In just 1 year of observations, it has begun to revolutionize our understanding of the early universe, challenging long-standing theories and opening new avenues for exploration. In the coming 5 to 10 years, there is a plan to further leverage the extraordinary capabilities of the James Webb Space Telescope to probe the intricate structures of the earliest galaxies formed in the universe. In a recent remarkable observation, the telescope has captivated astronomers with its depiction of a distant, vibrantly colored cluster of galaxies, whimsically nicknamed the Christmas Tree Galaxy clusters. In this cluster, known officially as MAX 416 and located approximately 4.3 billion light-years from Earth, the James Webb Telescope has identified 14 new transient objects. These are celestial bodies that experience a dramatic increase in brightness before eventually dimming. These transients, resembling flickering Christmas lights, contribute to the festive moniker of the cluster. Hang Yan, an associate professor in the Department of Physics and Astronomy at the University of Missouri, explains the cluster's unique name. MAX 416 is referred to as the Christmas Tree Galaxy Cluster not only for its colorful appearance, but also due to the transient, flickering lights observed within it. Transients are space objects, such as individual stars, that suddenly brighten significantly and then fade away. These objects shine brightly for only a brief period, making observations akin to looking through a constantly shifting magnifying glass. The remarkable observation of numerous transients in the Christmas Tree Galaxy Cluster was made possible by the combined efforts of the James Webb Space Telescope and the Hubble Space Telescope. The unprecedented number of transients detected simultaneously by these two powerful telescopes suggests that there are many more waiting to be discovered within this cluster, offering a sort of ongoing Christmas gift to astronomers. The light from this galaxy cluster embarked on its cosmic journey when our solar system, now 4.6 billion years old, was a mere 300 million years old. Normally, such distant light would be too faint for even the Webb telescope to observe in detail. However, a phenomenon first described by Albert Einstein in his 1915 theory of general relativity, has facilitated this observation. Einstein's theory, which delves into the nature of gravity, posits that objects with significant mass can warp the fabric of space and time, known collectively as space-time. This warping creates a curvature that we perceive as gravity. When any form of matter or energy, including light, travels near these curved regions of space, their paths are also curved. The closer an object is to this massive body, the more pronounced the curvature of its path. As a result, when an object passes between the Earth and a distant light source, the light from that distant object doesn't follow a straight path to us due to the curvature caused by the intervening object. This effect can alter the amount of time it takes for the light to reach us, making distant cosmic objects more observable. This phenomenon has been instrumental in enhancing our view of faraway galaxies like the Christmas tree galaxy clusters. This phenomenon, known as gravitational lensing, effectively amplifies the appearance of distant cosmic objects from our perspective. It occurs when an intervening object, such as a galaxy or a cluster of galaxies, acts like a natural cosmic magnifying glass. The James Webb Space Telescope has been exploiting this effect with remarkable success to observe some of the universe's earliest galaxies. Its observation of the Christmas tree galaxy cluster is a prime example of this. As Haiying Yan explained, the ability to see so many transients in certain regions of this cluster is due to gravitational lensing, which magnifies the galaxies located behind it. This rare opportunity provided by nature allows astronomers to get a detailed view of individual stars that are extremely distant. While currently only the brightest stars are visible, continued and frequent observations will enable astronomers to determine the number of bright stars and their mass. Yan and his team discovered these transients while analyzing 4 sets of images captured by the James Webb Space Telescope over approximately 4 months. This was part of the James Webb's PE-ARLSG TO1176 program. Among their findings, the team has identified 2 objects in the images as supernova explosions, marking the end of the life cycle of stars. Yan and his team are excited about these findings, as they provide a unique opportunity to study the galaxies where these supernovas are occurring. The 2 supernovas, along with 12 other extremely magnified stars, each have different characteristics, but all are significant to their research. By tracking the change in their brightness over time through light curves, the team aims to eventually determine the types of stars they are observing. In addition to these discoveries, the team uncovered something extraordinary in the Christmas tree galaxy cluster, a massive star in a galaxy size, as it appeared when the universe was just 3 billion years old. This star has been whimsically named Mothra, inspired by the monstrous moth kaiju from Japanese cinema. The galaxy hosting Mothra was lensed to about 4,000 times its original brightness. The nature of the object causing this lensing is currently unknown, but Yan and the team estimate that it has a mass between 10,000 and 1 million times that of the Sun. The most likely candidate is a globular star cluster, which is too faint to be seen directly by the James Webb Space Telescope. José Diego, the research lead author and a scientist at the Instituto de Física de Cantabria, noted in a separate statement that the true nature of this additional lensing object is still a mystery. Intriguingly, Mothra's galaxy was also visible and lensed in images taken by the Hubble Space Telescope 9 years ago. Normally, a lensing object and a background galaxy would move out of alignment over such a time span, but in this case, they have remained aligned, offering a rare and valuable opportunity for observation and study. In the future, Yan and his team aim to decipher the nature of the lensing object in the Christmas tree galaxy cluster and uncover some of its characteristics. By doing so, they hope to gain insights into the detailed structure of this cosmic magnifying glasses and its relation to the distribution of dark matter. This endeavor represents a novel perspective on the universe, made possible by the James Webb Space Telescope. In a separate line of inquiry, Scientists are exploring specific geological features on the largest moons of Jupiter and Saturn, which could be potential hotspots for the emergence of life elsewhere in our solar system. Researchers from the University of Hawaii at Manoa are leading a study focusing on strike-slip faults on Ganymede, the largest moon in the solar system, even surpassing Mercury in size, and on Saturn's moon Titan. These faults, similar to the San Andreas Fault on Earth, occur when walls of a fault move horizontally past each other. They resemble giant cracks or rifts in the ground. Such seismic features on these icy moons are thought to be the result of tidal forces generated by their massive gas giant parents. As these moons orbit their planets, the immense gravitational pull of the planets creates tidal forces that stretch and compress the moons, causing their surfaces to flex. These tidal forces are inconsistent due to the elliptical nature of the moon's orbits, adding complexity to the geological dynamics of Ganymede and Titan. The elliptical orbits of Ganymede and Titan mean that these moons are sometimes closer to their respective planets, Jupiter and Saturn, and at other times much farther away. This variability leads to stronger tidal forces. Leland Burkhardt, the lead author of the research and a scientist at the Hawaii Institute of Geophysics and Planetology, explained in a statement that they are studying shear deformation on icy moons. This type of faulting can enable the exchange of surface and subsurface materials through shear heating processes, potentially creating environments suitable for the emergence of life. On Saturn's moon Titan, surface temperatures hover around 290 Fe, 179 C, so cold that water on this moon behaves like rock, capable of cracking, deforming, and forming faults. The Cassini spacecraft, during its flyby of Titan, discovered that this Saturnian moon might harbor liquid water oceans tens of miles beneath its thick ice shell. Moreover, Titan is unique among solar system moons in having a dense, Earth-like atmosphere. This creates a similar hydrological cycle with methane clouds, rain, and liquids flowing across its surface to fill lakes and seas, making Titan a prime candidate for supporting life as we understand it. When NASA's Dragonfly mission reaches Titan in 2034, it will deploy a rotorcraft lander to traverse the moon's icy surface, searching for potential signs of biological activity. While this doesn't necessarily mean looking for conspicuous aliens, the mission aims at least to detect the presence of biosignatures or evidence of life-supporting chemical processes. The exploration of Titan by the Dragonfly mission is a significant step in our quest to understand the possibilities of life in our solar system. The research into the chemical building blocks of life, as we know them, is crucial, and the geological investigations by various teams are instrumental in guiding the missions of spacecraft destined to explore moons like Titan and Ganymede in our solar system. In a different venture, a team of astronomers led by Heinz Wilhelm Hubers, director of the German Aerospace Center, utilized the Stratospheric Observatory for Infrared Astronomy, SOFIA, an airborne observatory, to gather data on Venus's atmosphere. We were able to plan a flight route, which allowed us to observe Venus at a low elevation shortly before sunset for 3 consecutive days, each for about 20 minutes, explained Hubers. Aboard SOFIA was the upgraded terahertz heterodyne spectrometer, which played a key role in these observations. Hubers noted that this spectrometer is exceptionally sensitive to the frequency and wavelength of atomic oxygen, which are 4.74 terahertz and 63.2 microns, respectively. Venus's atmosphere features 2 distinct current layers. The lower one is situated below 70 km, or 43.5 miles, in altitude, where winds comparable to Earth's hurricane force blow in the opposite direction of Venus's rotation. The higher current is located above 120 km, or 74.6 miles, in altitude, with its own distinct wind patterns. This comprehensive study of Venus's atmospheric dynamics contributes significantly to our understanding of planetary atmospheres in the solar system. Between these 2 opposing atmospheric currents on Venus, there exists a layer of atomic oxygen. Huber explains that this layer is believed to be formed by ultraviolet radiation from the Sun, which breaks down carbon dioxide and carbon monoxide in Venus's atmosphere into atomic oxygen and other molecules. This process, known as photolysis, involves high-energy photons colliding with carbon molecules, causing them to split apart. This atomic oxygen is primarily concentrated around 100 km, or 62 miles, in altitude, situated between the two circulation patterns. The team suspects these currents might play a role in distributing this substance around the planet. However, Huber mentions that they couldn't fully quantify this with their current measurements. Interestingly, a local increase in atomic oxygen was observed on the night side of Venus, near the terminator, the line that separates day from night. This enhancement might be influenced by the winds at the terminator. It's noteworthy that the concentration of atomic oxygen in Venus's atmosphere is significantly lower than that of Earth's. Earth's atmosphere contains about 10 times more atomic oxygen than Venus's. On Earth, this high concentration of atomic oxygen is known to contribute to the corrosion of satellites in low Earth orbit, including the International Space Station. Therefore, the lower concentration of atomic oxygen on Venus implies a reduced corrosive threat to any future satellites sent there. Understanding the distribution of atomic oxygen in Venus's atmosphere is crucial for comprehending the chemistry and physics of the atmosphere and for drawing comparisons with Earth's atmosphere. As Huber concludes, these measurements are vital for a deeper insight into the atmospheric dynamics of Venus. Huber's emphasizes the importance of collecting data from both the day and night sides of Venus, especially considering the planet's extremely slow rotation. A single day on Venus lasts 243 Earth days, or 5,832 hours. The most plausible explanation for this sluggish rotation, as per Huber's, is the gravitational influence of the Sun. In Venus's early stages, when the planet was in a more fluid molten state, solar gravity induced tides on Venus. The rotational energy of Venus, combined with its then molten structure, likely worked against these tidal forces, gradually slowing the planet to its present rotational speed. The findings from this study paint a picture of the Venusian atmosphere that is markedly different from Earth's. They underscore how seemingly minor differences in planetary history can lead to vastly divergent futures over time. Welcome to Blisovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. This concludes the information for today. The support and feedback from viewers are greatly appreciated, as they motivate the continued delivery of quality content and the pursuit of improvement. Don't forget to give a thumbs up if you enjoyed today's episode, subscribe for more updates, and hit the bell icon to stay informed about future episodes. Your thoughts and opinions about today's content are highly valued, so please share them. Thank you for watching, and we look forward to seeing you in the next episode.